In our last podcast, we were talking about Dalton's atomic theory. That was the first modern atomic theory. And it was really simple, right? He just reacted stuff together. He measured it before and he measured it after, and he found that things always reacted in set ratios. So that led to a bunch of ideas. The ideas of conservation of mass, the ideas of laws of definite proportion. But it wasn't completely right, because Dalton, of course, was thinking about atoms like this. He was thinking that this is an oxygen atom and that it's uniform. And actually, he didn't even like the idea that atoms could bond to themselves. So he was thinking each of these elements, each of these different atoms of different elements were basically spheres that could bond to other spheres, but in themselves they were just a sphere. But that model is going to fall apart here pretty quick. It's going to fall apart when we find this man called J.J. Thompson. And we're not really concerned about names, but we'll write his name down since he did something pretty big. So we have J.J. Thompson, and what he did was he just ran electricity through inert gases. So he put gases into a glass chamber, so very much like this. So this is a sealed glass chamber that has a neutral gas in it, okay? So it just has gas in it. That's all. But all of a sudden, he hooks up a cathode and an electrode. So electricity was getting really popular, and people were playing around with electricity. You'll notice he's holding the alligator clip there in his hand, and they're just sending electricity through substances and seeing what's happening. People really didn't know. These were truly experiments. But what he saw is he saw a beam of light within that inert gas, which was crazy because, again, it was just inert gas. There was nothing there. If atoms were spheres, well, we're seeing something else, right? We're seeing some destruction of those atoms. Something is breaking apart. And how they could see this beam is this is actually a phosphorescent screen, so it's causing it to glow here a little bit. So let me erase some things and we'll take a look at what he was looking at. So he has this beam going across. And at first, people thought maybe perhaps, looking at this one, they thought perhaps it was just light, and people came around and they looked at it. But he had the ingenious idea then that what he did was bring a magnet up to this beam of light. Well, this beam of light then bent towards the magnet if they held the positive sign towards it, or reversely, if they flipped that magnet around and held the negative sign towards the beam, well, then it would deflect the beam and push the beam away. So this led J.J. Thompson to a couple different conclusions, two conclusions. First conclusion was that there was stuff inside the atom. So the atom wasn't it. There was what we could call now subatomic particles inside of atoms. So there's stuff inside of atoms. Two, they're negatively charged. They're negatively charged because, again, the experiments with the magnet, and they could also find their mass, and they found that they had a mass. So they're negatively charged. They had a mass, I'll add that, but their mass was very, very small. So what his idea then revolutionized the atomic theory, brief revolution, to have what was called the Plum pudding model of the atom, where there's negative particles, what he called corpuscles, but nobody calls corpuscles. They call them electrons. Corpuscles didn't stick, but they're negatively charged particles within the atom, and the atom itself was just an ooze, this positive ooze, but you could kick those electrons out with electricity. And most of us were kind of wondering what a plum pudding model really means, because we don't eat much plum pudding here in the States, but this is a nice image of plum pudding, so you can see the electrons sitting in that plum pudding and the cake itself. Notice not really a pudding, more of a cake, but we do have our electrons sitting around floating kind of within that positive ooze. And that model was good for a little while, until, again, it was tested. So the next test was Rutherford's gold foil experiment. And so he wanted to test that structure of atoms. And so what he did was he took a sample of gold foil. And the reason he took gold foil is because gold is very malleable, like all metals, and can be pounded very, very flat. So that is just a few atoms thick. Well, it's not really a few atoms thick. It's a few hundred atoms thick. But it's the smallest, thinnest piece of matter that he could make. So he got this piece of gold foil. And really, this image isn't doing much justice at all. I should just erase it. But a really, really thin layer of gold. And what he wanted to do is just see what effect that had on an array of alpha particles. So not really knowing what alpha particles are, just knowing that they came from a radioactive source. So they got a radioactive source in a lead box here, had a little hole for those alpha particles could come out. Those alpha particles came out, struck the gold foil, and then again they had that phosphorescence sensor around so that they could detect where those alpha particles hit. And again, not having a lot of knowledge of alpha particles, just knowing that they're these charged, positively charged heavy particles. What we know now is they're just a helium nucleus. So they're a helium nucleus, a helium that's been stripped of its electrons. So really it has the mass of 2 protons. So in their eyes, a big, heavy, positively charged particle is flying at this gold foil. Now, if we think about it like plum pudding, and you're shooting other plums at this, well, they should all kind of react basically uniformly when they strike this plum pudding. Maybe some will get bent a little bit, but again, if this is our model of the atom, there's not a lot there to affect these big positively charged alpha particles from shooting right through. Maybe they would kick out some electrons. We don't really know. That's why, again, it's an experiment. Well, what he saw was that instead of cutting through nice and uniformly like would be predicted, what they saw is still the vast majority cut through. So the vast majority, like 99.9% of the particles went straight through. So most went through. Really, the vast majority did go through. But a few were bent a little bit, which was interesting. So if they had the sensor right here, they saw all these blinks, all these particles coming through, held it to the side, you'd occasionally see a blink. And then if you put it back here, you'd see nothing, almost nothing, except for randomly, there'd be a spark. Not a spark, but a nice shine coming back there. So that's telling us occasionally, very occasionally, just a fraction of particles are reflected exactly backwards. So that was crazy. That led them to this more advanced model of the atom. So if most of them are going through, most of the alpha particles are traveling through, what that is telling us is this, that most of the atom is empty space. There was no deflection at all. The vast majority, again, 99+% are going straight through. Some are getting deflected at some angles. Well, if we have this positively charged particle flying in and it gets deflected, that means it's being bent. So it's running into something else that's positive. So some alpha particles are deflected at small angles. So that's telling us there's something positively charged there's concentrated positive charge. So the positive charge can't be an ooze. We can't have negative particles within a positive ooze, so red positive ooze. We can't have that because the particles aren't uniformly deflected. There's only a few deflected. So that's saying there's concentrated positive charge. And when only a couple bounce back, that occasional alpha particle being shot straight back is telling us that not only is that positive charge concentrated, but it must be very, very massive. So there's this tiny, massive positive charge in the middle of the atom, or relatively in the middle, with the electrons outside. This is our new Rutherford model of the atom. And again, there's some great videos on my website that show both this experiment and give you a scale of how tiny that nucleus is within the atom. So again, here's our idea. And all of these diagrams kind of mislead you because they show the nucleus being relatively big and they show you a lot of backwards deflections. And really, the deflections were so minor. The vast majority, again, 99.9+% of the particles went straight through, the vast majority, telling us most of it's empty space. There's a few deflections, and then only occasionally did one ever get bounced back. Okay, so that gives us this kind of model of the atom, that inside we have a nucleus that's very, very tiny, but very, very massive. So it has a mass of what we are calling one atomic mass unit. We call them AMUs. It's an atomic mass unit. Later on, they would discover that there was some mass unaccounted for that must also be in the nucleus, and those were called neutrons. And it took them a while to find them because they're neutral, so it's a lot harder to find things that don't have charges. They knew the mass was off, A neutron was theorized for a long time before it was eventually found and discovered. So also having a similar mass. So we have protons that are positively charged in the nucleus with some neutrons that are have zero charge, same mass, one atomic mass unit. And then we have on the outside, thanks to Rutherford, electrons that are negatively charged, and says the mass is nearly nothing. Well, nearly nothing is about 1/1800th of an AMU. So there is a mass in the electrons, but the electrons are tiny, really low mass, but they are negatively charged. So I'll skip a couple of these here. So this is our modern kind of idea of what our subatomic particles are, our basic subatomic particles. We have protons that we have a symbol like this for. They have a mass of 1 AMU, a charge of +1. Neutrons, neutral. Sometimes we put a little 0 here above that end, say neutral. So electrons, 1/1800th or 1837th, and charge of -1. Now the next advancement in our atomic theory is really from Niels Bohr, who we'll talk about more when we start talking about electrons, but he told us then that not only are these electrons outside of the nucleus, and this is showing a really large nucleus. All these models, again, are models. They're not accurate representations because we can't make an accurate representation due to how small that nucleus is. But he gave us the idea that not only are these electrons outside of the nucleus, but they're in set arrangements, set orbitals, so set energy levels, perhaps we'll say. So they're set energy levels around that nucleus where the electrons are in. So they're in what we'll call orbitals. So they're in set energy levels called orbitals that are orbiting about the nucleus. And this gives us our kind of our planetary model of the atom that, again, we're going to tear apart when we go into our unit on electrons. But for right now, it's okay to think about our atom as a planetary model, with protons and neutrons being the most massive particles in the center and our electrons orbiting outside in our orbitals. Now, you may know and have heard of things called quarks, and there's subatomic particles beyond quarks, but you may have heard of quarks. Well, quarks really are the subatomic particles that are within our protons and neutrons. And so, again, much smaller than our protons, but protons and neutrons consist of what are called up and down quarks. And notice these are very, very small. This is 10 to the negative 19th meters, even smaller than what we'd consider an electron size to be. But we're not going to really go there. I just want you to be aware that those do exist. So the subatomic theory, how it goes a little bit further in breaking things down. So at one time they thought atoms were the smallest pieces of matter, and then for a long time we had a nice model of subatomic particles, which is protons, neutrons, and electrons, which is as far as we really need to be concerned as far as chemistry goes, because that's where all our chemistry happens. But again, if we go into particle theory, we can break that down even further into quarks and other types of subatomic particles, subatomic particles, perhaps.